Okay, our next speaker is Ido Tal, who's very well known for his work on list decoding of polar codes. I hardly have to emphasize how much of an impact this has had on real applications. So he's going to talk to us about deletion channels and substitution channels. Take it away, Ido.
I'm very happy it's been recorded. Okay, so my talk is titled Polar Codes for Channels with Insertions, Deletions, and Substitution, and it's joint work with Henry Da, which is my master's student, Alman, and the late Alex Barty, which I miss dearly, and I guess many in the audience do as well. So the talk has polar codes in the title, but I'm going to try and make the case that many of the ideas I'm going to be presenting here are general, in the sense that they're not specific to polar code. So hopefully this talk is useful for a large audience. I'm going to split the talk into 3 parts. So in the first part, I'm going to show you a coding scheme for the deletion channel, only the deletion channel for start, no insertions or deletions, with probability of error going down like roughly 2 to the power of minus the code word length cube root. And the tricks are the following. We're going to add what I call guard bands. These are sequences, long sequences of zeros inside the key places in the code word. Okay. These will allow me on the decoder side, these guard bands are going to allow me on the decoder side to break the received word into blocks. It's going to be important for synchronization. For each block, I'm going to define a trellis, which will help me keep track of the relevant probabilities and also do minus and plus transforms. And I'm going to define a bespoke channel, which I'm calling the trim deletion channel, in order to analyze this coding scheme and prove that the probability of error is this. Okay, so this is going to be the first part. The second part, I'm still going to talk about the deletion channel, only deletions, but now I'm going to show you how to get the error down to roughly 2 to the power of minus square root of the code word length. That's the second part. Some ideas are going to be copied from here. I'm also going to be using guard bands. The trick is, instead of breaking the received word into blocks and having a trellis for each block, I'm going to be using a big trellis for the whole received word. So that's what's going to allow me to get a better probability of misdecoding. And surprisingly, for the analysis, I'm going to use this trim deletion channel, which was kind of natural for the first part, but doesn't play any explicit role in the decoding algorithm here, but still turns out to be very useful for decoding for some reason, for analysis, sorry, for some reason. And in the third part, I'm going to generalize to the insertion, deletion, substitution channel. Okay, and there I'm going to show you that I can have a coding scheme with probability of error roughly 2 to the power of minus cube root of the code word length. So this slide begs the question, can I do 2 to the minus square root of the code word length for the IDS channel? And Da has been working on this, and we believe that the answer is yes, but we still need to iron out all the details. So for now, this is what I can promise you for the IDS channel. Okay, so let's start with the first part. What do I have? Let me give you the big picture first. I'm going to assume that the deletion channel. I'm going to assume that this deletion channel has a constant probability of deletion delta, so it doesn't go down with the code word length or anything like that. It's constant. I'm going to fix some hidden Markov input distribution, where I need the Markov chain to be aperiodic, irreducible, and finite state. The code rate, which I'm going to get, is going to converge to the information rate between the input vector x and the corresponding vector y. I need to talk about information rates because we have memory, right? It's a Markov process, so I have to talk about information rates. And it turns out that because I can use a rather large family of input distributions, I can approach the capacity of the deletion channel by using a sequence of input distributions. Okay, So for now, I'm going to show you that the error probability decays like 2 to the power of minus lambda to the power of gamma, where gamma is any constant less than one third. So almost roughly cube root, 2 to the power of minus cube root of the code word length. Gamma less than half we're going to show later on. And decoding complexity, at the worst case, is O of code word length squared. So this is worse than what we get for Arikan's seminal polar codes, but maybe this is the price we have to pay for working with such a hard channel like the deletion channel. Okay, key ideas I talked about, but maybe I should repeat. We're going to be using trellises to keep track of the probabilities, and we're going to modify the standard output of Arikan's polar encoder by adding guard bands to it. Okay, so I had a very nice segue from Moshe, who talked about run length limited constraints. Here's an example of an input distribution I can use. Okay, so what do we see here? We have two states, and in this example, if this state outputs a 1, if I output a 1, then next symbol I have to output is 0. Okay, and I have to output at least 1 0. I could output a few more, and then again, I'll output a 1. If I output a 1, next symbol is 0, and so forth. Alpha is the probability of outputting a 0 if I'm at this state. 1 minus alpha is the probability of outputting 1. I claim that you've seen this constraint before, almost. Can you see it? So Moshe was talking about a 0-1 RLL constraint. 0-1 means that between any two ones, there is at most a single 0. If you just do the naught of the bits, you get this constraint. Just switch the roles of 0 and 1. So this is one example of an input distribution I can use. I can use any RLL input distribution, anything which can be represented as a Markov chain, which is aperiodic, right? It's aperiodic because here I have a cycle of length 1. It's connected, and it's stationary. Okay. And maybe I should just stress that I only get to see on the, I don't at any point assume in the decoding, I never assume that I know the state. Okay, so the state is hidden from me when decoding. I'm not cheating. Okay, what's the code rate I can achieve? Well, I have to talk about information rates, right? I have to talk about a vector x of inputs and a corresponding vector y of outputs. So x, if x is a vector of length n and it's a deletion channel, so typically y is going to be a vector of length less than n. Okay. So this is the rate I'm going to be able to achieve for my fixed input distribution. Let's see how we do this. So here's the theorem that I'm going to prove. I've basically said this before. I fix the constant gamma. I fix an input distribution, and for a large enough code word length lambda, this is the error rate I can get. Okay. Yeah. Yes.
Just to understand this result, you're saying that with this you get a bound on capacity. It's not the actual capacity of the, because I think there is people by sparse Ido Tal where they had this type of model, like they had a Markov input sequence and they estimated the capacity of deletion. So you're saying whatever is the information rate with this type of Markov, that is achievable by polar codes.
Right. And it also turns out that I can have a sequence of these types of input distributions. I can't give you it specifically, but I know of the existence of a sequence of input distributions where the information rate is going to approach the capacity of the deletion channel. Okay, so it's a fine point, but.
So this type of inputs are actually optimal for the deletion channel. Can I interpret?
Yes. Yeah, in the limit, right? There's no, we don't know that there's a specific one, but you can get arbitrarily close.
It's very interesting.
Thank you. Okay. So yeah, I've been trying to make the point that I can use a kind of a large, rich family of input distributions, and they have nice properties. But for the purposes of keeping this talk simple, I'm going to assume the simplest possible input distribution. Namely, I'm just going to assume that the xi's are IID and Bernoulli Hef. Okay, just to keep the notation light and hopefully get the main points across. Okay, so this one slide hopefully will give you all the background you need for understanding, in terms of polar codes, for understanding this first part of the talk. So I'm going to define the minus transform and the plus transform and then the polar transform. Okay, so what do I start with? So I have a vector x of length capital N, where capital N is 2 to the power of lowercase n. And both the minus transform and the plus transform take this vector of length n and return a vector of half the length. So x, the minus transform, just gives me back the XOR of consecutive odd and even entries of x. So it's x1 XOR x2, that's the first entry, x3 XOR x4, that's the second entry, and so forth up to xn minus 1 XOR xn, so obviously half the length. Okay, so that's the minus transform. Plus transform is even easier. Okay, it just gives back the even indices of x. Okay, so that's the minus transform and the plus transform. I can do this over and over again. Okay, so if I start with a vector of length 2 to the power of lowercase n, if I do a sequence of n minus and plus transforms, what do I get at the very end? Just a single bit, right? Just a vector of length 1. So I can do this over and over again. And this is the way I define the polar transform. So a polar transform takes x, a vector of length n, produces u, a vector also of length n, where entry I, ui, is gotten by taking x and applying a sequence of lowercase n minus and plus transforms, where what's the sequence? Well, the sequence is determined by the binary representation of the index I. Okay, so hopefully this is all you need to know to understand the first part. Okay, so I have a minus transform, a plus transform. I apply them again and again, and this is what allows me to define the polar transform. Okay, moving on. How does a polar decoder work? Well, in order to implement a polar decoder, you have to be able to efficiently calculate probabilities of this type. Okay, so you have to be able to calculate the probability of ui equaling some bit, 0 or 1, conditioned on previous decisions you've made on previous entries of u, and also you also condition on the y, the word that you've received. Okay, so this is something I need to be able to calculate. And as a first step, let me show you how to keep track of the joint probabilities of input and output. Okay, no polarization transforms yet. So how do I do this? A very convenient way of doing this is by using a trellis. So here's an example. Let's see what we're seeing. Let's understand what we're seeing here. So now we're on the decoder side. Okay, I know that I've been sent a word of length 4, and this is the word I've received. So 0, 1, 1, a word of length 3. So there was one deletion, right? Okay, so how do I keep track of this? Well, you'll see that you have you have edges of two colors, right? There are blue edges here and red edges here. And there are also two types of edges. There are horizontal edges and diagonal edges. So a blue edge means that the corresponding input is 0. So blue is 0, red is 1. This, if I traverse this edge, it means that x1 was 0. If I traverse this edge, it means that x1 was 1. Okay, if I traverse, say, I don't know, this edge, it means that x3 was 1. 1 is red, yes. Okay, so that's edge colors. And now, let's talk about horizontal versus diagonal. If I traverse this edge, the horizontal edge, this means that x2 was 0 and it was deleted. So horizontal is deleted. This edge means x2 was 1 and it was deleted. And this edge, a diagonal edge, means that x2 red 1 was a 1, and it did not get deleted. Okay? So x2 made it through the channel and was observed as y2, which is also 1. Okay? This edge means that x3 made it through the channel, it was a 1, and it's received as y2, which is also a 1. Okay, so hopefully that's clear. If there are questions, this would be a good time to ask. No.
Well, I guess the dashed lines are things that you're not, we're only interested in the solid paths. From
Exactly.
the upper left-hand corner to the lower right-hand corner.
Right, exactly. We're not interested in the dashed lines. Why are we not interested in this edge, for example? Because if we were to traverse this edge, that means we had 2 deletions. Okay, but we've sent something of length 4, we got something of length 3, so we can't have 2 deletions, right? So exactly as you said, we're only interested in the solid lines, the dashed lines we can forget about.
Question, so you had like 4 by 2, then you would have the trellis would be, the solid trellis would be twice as wide, but
If you had 4 by...
yeah, Y1 and Y2, if there was no Y3.
Okay.
So then the solid section would get a little wider.
Right. Right. Because then you would, here you're only allowing for just the 1 deletion. In your example, you'd be allowing for exactly 2 deletions. Yes, thank you. Good question. Okay, so this is all we're interested in. How much time do I have? Wow, that's fast. Okay. Now I can assign a probability to each edge. Okay, so let's see. What does this edge correspond to? It corresponds to x2 being 1 and getting deleted.
It's 11:37.
Yeah. Okay, see, Eitan, I don't need to haggle because you've done it for me.
Behavior gets reward.
You're welcome. Okay. Okay, so what about this edge? Red means x2 was a 1 and was deleted. So what's the probability of such an event? Well, we're using a uniform input distribution. So x2 equaling 1 happens with probability half. The probability of it getting deleted is delta, right? So delta over 2. What about, I don't know, this edge? It's also red, right? The probability of x4 equaling 1 is 1/2. And a diagonal edge is an edge that was not deleted. Okay, so what's the probability of not getting deleted and being 1? Well, it's 1 minus delta, which is delta bar, times 1/2. So this is the probabilities corresponding to the examples we've shown. And now recall that in the minus transform, we don't really care about the actual values of x1 and x2. We only care about their XOR. So now, let's see, what's the probability of getting from this point, this vertex to this vertex with a red edge? That is, with an edge, I'm sorry, what's the probability of getting from here to here and having the XOR of x1 and x2 being 1? Okay, so this is this edge, right? Getting from here to here and having the XOR equaling 1. 1 is red. So how can I do that? Well, either x1 was 1 and it was deleted, and then x2 was not deleted, or x1 was not deleted, it was 0 and not deleted, and then x2 was 1 and deleted. Okay, so it's this times this plus this times this, which is exactly this. Okay. Now I can prove what's called weak polarization. This is rather straightforward by now for people who know about polar codes. This is nice, but this is not enough in order to prove to claim a coding scheme. What I need to do is to show strong polarization. So how do I do that? Well, let's denote by n naught, gamma times n, where you'll recall that gamma is this constant which is less than 1/3. N1 is 1 minus gamma times n, okay? And define capital N naught and capital N1 as 2 to the power n naught, 2 to the power n1. Now, let's look at these series of n1 blocks. Okay, each block is of length n0. So the total number of bits here is capital N. I've just segmented it into blocks. Okay. Now, the channel input, suppose that it's just the concatenation of these bits, these blocks. What do we see on the decoder side? Well, on the decoder side, we just see the output corresponding to x1, which we denote y1, the output corresponding to x2, which we denote y2, but these outputs are concatenated, right? So that's a big problem with deletion channels. We don't get a nice separation of y1 and then y2 and then y3 with a nice comma in between them. We only get the concatenation. Now, if only I had a genie that instead of giving me this, would give me y1 comma y2 comma y3 and so forth, then my life would be very easy. Then for this setting, it's very easy to prove strong polarization. Of course, we're not in this setting. Okay, so how do we get to this setting? We want a genie, okay? We want a genie that gives us punctuation marks. Well, you don't always get what you want, but you'll get what you need. We'll settle for this genie. What's the problem with this genie? Well, he's missing a head, as you can see. And he's also missing a tail. Okay? So this genie has no head and no tail. So here's what we actually see. Here's what we want the genie to give us. And here's what we'll settle for. This is the good enough genie. So the good enough genie is going to give me a comma-separated list, not of y1, y2, yn, up to yn1, but y1 star, y2 star, yn1 star. What is star? Star is removing leading and trailing zero symbols. Okay, so no head of zeros, no tail of zeros. That's the cartoon from before. And asymptotically, I'm not losing anything because mutual information between x and y star is basically the same thing. Removing a bit of zeros from those beginning and end doesn't change anything. Okay, how am I going to, well, I wish I had such a genie, but wishing doesn't really help us. So we have to build such a genie. How are we going to build such a genie? Well, we're going to introduce guard bands and then use them on the decoder side. So what are we going to do? X is the output of a standard Electron encoder. Okay? And we apply, before transmitting, we apply on X the function G, which adds guard bands. So G is a recursive function if X is short enough. So if the length of X is at most 2 to the power of n naught, we just return X. If it isn't, then we stick a guard band, a bunch of zeros in between of length Ln, this is Ln, and then apply G recursively on the left half and the right half. Okay? So here's an example for n equal n naught plus 2. This is the first guard band we put in, then G recursively adds this guard band to the first half, this guard band to the second half, and then stops, right? Because we have 2 stages of the recursion. Okay, so how does this help us kind of implement our good enough genie? Well, here's what we do. What do? We take X, we blow up X into G, having guard bands. This is what we get on the received side, okay? And now how do we affect the genie? So the first thing the genie does, okay, this is a man-made genie, okay? This is me, the genie. I'm going to be the genie with very high probability. So what am I going to do? The first thing we do is we take Y, remove from Y leading and trailing zeros. That gives us Z. Now what we do is we take our finger and point it at the middle of Z. Now, with very high probability, we've landed in something that comes from a guard band. Okay, so with very high probability, these are just a bunch of zeros. So if we take this, trim all these zeros and maybe some zeros, leading zeros here, call this the first block. Do the same thing here. We trim all these zeros, and maybe some leading zeros here. Call this a second block. Then we've chopped up Z into 2 blocks, and now we can do the same thing recursively for the first block we got and the second block. Okay, so this is our way of implementing the good enough genie. Okay, and now this we're going to succeed. When are we going to succeed? Well, we're going to succeed if at each and every step we land in Z triangle, which came from the outermost guard band, and this is going to happen with very high probability. Okay, so that's basically the trick. Once we do that, then we're all set. We've punctuated into blocks of Y star, and it's very easy to prove strong polarization. Okay, I'm not going to use all the time, but let me take a few more minutes. Now let's see, how do we get from gamma less than 1/3 to gamma less than 1/2? Well, some ideas are going to stay with us. Previously, we had this step of breaking up the output into blocks and having a trellis for each block. Now we are going to have a big trellis for the whole received word. We're not going to break it up into blocks, okay? Because that's kind of an error-prone step. We're not going there. So we're going to decode with just a big trellis on all the received word. There's a complexity hit associated with that. It's still polynomial, lambda to the power of 4. And now the question is, how do we prove that the probability of error is better? So what I typically need to do is talk about the Bhattacharya of ui, given past u's, and my received vector y. Okay? Turns out, I don't know why, but it turns out that I should look at y star. Okay? This is a processing of y. So this Bhattacharya is only worse than the Bhattacharya I'm really interested in. So I'm looking at y star instead of y, even though there's no, in this second algorithm, there's no natural way in which y star enters the thing. I'm still looking at y star. And now I'm saying, well, suppose I take this y star and I want to chop it off into 2 blocks, like I've done before. Again, I never do this in this second decoding algorithm. But suppose I wanted to, then I can bound this, upper bound this by the Bhattacharya of ui given past u's, the y star of the first block, the y star of the second block, plus some additive term which has to do with the probability of not landing in the right place and not chopping up y into 2 blocks. Okay? Getting from here to here is kind of standard polar codes, and it's what I get is a recursion which is almost kind of well known, but there's this additive term which doesn't appear in Ali Khan's paper. Okay, it turns out I can still prove everything I want with this additive term. It's very small. Okay, and that's what allows me to do to get to gamma equals 1/2. Okay, I'll just very quickly talk about the insertion deletion substitution channel. Here the trick is a bit different. This is the most important slide. What's happening here, again, I'm going to have guard bands, but now they're going to be more elaborate. Right? Previously, the guard band was just a bunch of zeros. Here, the guard band is zeros, a bunch of zeros at the end. It's always the same length of zeros. But in the middle part, I'm going to have a bunch of ones. Okay? And now, how do you break things into blocks? Well, it's more elaborate. You put your finger in the middle. Typically, you end up somewhere here. How can you differentiate between being here and being here? Well, here you're going to typically see more zeros than ones than here, right? Because here it's ones. Some were deleted, some were flipped, but mostly you're going to see a lot of ones here and a lot of zeros here. Here, after you pass the channel, that's basically what you use to chop things up into blocks. Okay, but before we were removing trailing and leading zeros for y. Here now we're going to add some garbage before and after y, but it still works. Okay, thanks.
We have time for a couple of questions.
Yeah. So what's the total overhead of
So I can play with the parameters to have the total overhead be basically 0. Let me show you. So I take epsilon, some constant, I fix it to be small. Okay, so imagine it's 0.1. Okay. So this is of length 2 to the n, this is of length 2 to the n, and this is of length 2 to the 0.9 times n minus 1. Okay. So this is much larger than this.
But where is the dependence on the delta, on the deletion problem?
Here you don't need it. You fix some small constant and it works. I mean, I have to look at the paper. I'm pretty sure, but this epsilon basically in the asymptotics doesn't depend on delta. Just have it some positive number which is not 0. That's it. Yeah.
For the insertion deletion version, when you point your finger, you're gonna try to do. You have to estimate the band there that's not all zeros. You're gonna do some sequence distance.
So I'm going to do something very simple. I'm going to have I'm going to look at a window. Okay, so here I'm somewhere in these ones. Okay, and they're corrupted, right? So it started out from ones, but some got deleted, we had insertions. This 0 maybe is a substitution, maybe it's because of an insertion. But what I do is I take a window, okay, and I just count how many ones I see in the window. And I shift it until I see more zeros than ones. And when I see more zeros than ones, that's where when I guess that I'm in this thing that comes from the zeros at the ends of the guard bands. Okay, and then if I get to this point, I just remove everything from here, and this is the garbage I get from the left, kind of added to the left of my block. That's it.
So you only delete the mostly ones part and leave the mostly zeros parts at the end?
Yeah. So the garbage is a corrupted version of the zeros, which I've said, which is short. Okay.
But this goes back again to Emanuele's question, right? How does this play with the probability of insertion and deletion? Let's say the probability of inserting the 1 is very high, right? Then maybe this wouldn't necessarily work.
So again, I didn't have time, but I'm assuming some symmetry. I'm assuming that where was it? Yes. So I'm assuming I have some advantage of seeing a 0 if I put in a 0. So alpha 0, 0 is the expected length of zeros I get when I input a 0. Okay, think of a channel as getting a bit after a bit after a bit and outputting nothing if it's a deletion, outputting x if it's not a deletion, x not of x if it's a substitution, and so forth. So alpha 0, 0 is the probability of, is the expected number of zeros I see at the output if I input a 0. This is the expected number of ones I'm going to see if I input a 0. And my constraint is that I'm going to expect to see more zeros if I put in a 0. Okay? And then this works, right? If things are symmetric. Deletion, if you're deleting, then a bunch of zeros, you're going to expect to see more zeros than ones. If there's a substitution, if PS is less than 1/2, right, then you're going to flip Not typically, you're going to see more zeros if you put in a 0. Okay. Insertion, I've here assumed that it's symmetric, right? So the probability of inserting a 0 and inserting a 1 is the same. Okay. And if I have no error, then obviously, right? I put in a 0, I got a 0. It works. And I should be fair and also say that I'm expecting the total length to not be a function of what I put in. Okay. So the total length of what I get out when I put in a 0 is assumed to be the total length of what I get out if I put in 1. Okay, so these are kind of symmetry conditions which I assume. Yes.
The slide where you were talking about the size of the guard bands, and you have the 2, it's 2 to the 1 minus epsilon times n minus 1. So, I mean, if epsilon is small, do I understand right that you're going to use about half of the block length?
No. It's because it's in the exponent. Let me show you sorry. Let me show you the expression, and then you'll see. Where is it? Stop me. That's right. Here, right here. So it's 2 to the power of 1 minus epsilon times this. Okay, so it's not if 1 minus epsilon was here, then it would be of comparable length, but it's here, it's in the exponent.
Yeah.
So that's my trick. And I should also tie in with Eitan. You talked about your biology friends, right? Who said they want 40% of this and 60% of that. This is kind of a natural thing to impose with an input constraint. So my input constraint also allows me to have 40% G's and okay. This is binary, right? But I can generalize it to alphabet size 4, and I can play with the probabilities here to have 40% of this and 60% of that. It works.
Okay, one last question.
I might have missed it, but why do you want to add 1s into the guard band again?
Why do I want to? Oh, for this is I want to add 1s only for the insertion deletion substitution case. Okay, because I want to be able to understand when I'm close to the block. I don't want to kind of remove things from the block. Previously, in the deletion case, I was removing leading and trailing zeros, which is fine. Okay, but generally, I don't want to remove arbitrary stuff from the block. So I stop just before. Right, I see I'm here. This is my window. I see, a majority of 1s, a majority of 1s, a majority of 1s, a majority of zeros. Okay, a majority of zeros means I'm in this second kind of in this region here. So let's stop here, remove all these, but the stuff here, some of it is zeros from here, and the rest is from the block. So let's not touch that.
Thank you.
Sure.
All right, thank you very much.